Welcome to Making Sense of Complexity, featuring conversations with complexity science practitioners and philosophers. Our goal with this series is to share insights on how to make sense of our complex and uncertain world. Today, our guest is Dr. Klaas Landsman, a professor of mathematical physics at Radboud University in Netherlands, and winner of the Spinoza Prize in 2022. We were introduced to Klaas by an earlier guest, Nasa Janovsky, who remarked that Klaas is a superstar in the world of theoretical physics. He has been deeply immersed in its mathematical complexities for decades, and preparing for this conversation was very challenging, as we try to make sense of two profound questions: his final proof that quantum physics cannot be deterministic, and how do we explain the phenomenon known as cosmic fine-tuning? We'll be citing 3 of his works, and there are links in the show notes. Let's give it a go.
Klaas, welcome to Making Sense of Complexity.
Welcome. Thanks, George.
Yeah. So where are you calling in from today?
So I'm living in Nijmegen, which is a place just in the center of the Netherlands near the German border. I am from Amsterdam, that most of your listeners will have heard of, but I'm in Nijmegen. It's in fact the oldest city in the Netherlands. It's 2,000 years old.
That's a lot older than any place in the U.S., for sure,
Yes.
Any of our modern cities. And what's the weather like?
It's cloudy, but not rainy. So typically in Holland it rains, but it doesn't at the moment. It's very pleasant, in fact, at the moment. So,
Good, a good day.
Yeah, it's a good day in many ways.
Yeah. So it's a good day for a conversation on complexity, and I really appreciate your time and your expertise. And I did get a chance to look at some of the materials I've written, quite extensive. I put 3 citations in the show notes. One of them is the textbook you wrote in 2001 on the foundations of relativity. And I noticed that book was dedicated to Roger Penrose, who won the Nobel Prize in Physics in 2020. He's one of my personal heroes as well. And you have a personal relationship with Roger and have met him. And I wonder, what do you feel is so special about him?
So first about his work. So I would say he created most of the mathematics necessary to deal with black holes and also with the Big Bang in a way that went far beyond Einstein. So the theory he's famous for his work on is general relativity, the theory of space and time and gravity that sort of governs the universe, including black holes and the Big Bang. And Einstein left it at a certain point, which wasn't enough to really proceed to the really deep questions about singularities and event horizons and so on. And from the late 1950s onwards, Penrose took it from where Einstein left it. And I would say all modern research in general relativity that is sort of serious mathematically is based on his idea. So there's immense creativity in his mathematics, and as a mathematical physicist myself, I would also say it's incredibly difficult to be both mathematically precise and physically relevant. Few people can do that. I would say Newton, von Neumann had a hand at it, and also Penrose. And also he's a very nice guy. I mean, for someone of that caliber, I mean, he's amazingly friendly and modest. And also very energetic. So the last time I saw him was July last year, and we talked and walked for 3 hours. And he was 92. He's very generous, very friendly, and yeah, he's certainly, I would say, my hero in science.
Oh, that's wonderful. Yeah, so that is something to aspire to for all of us to be.
Yeah, there's one thing I forgot to say. His playful side includes his almost professional level drawings. So his scientific drawings are amazing. So he has the craft of a professional artist.
Yeah. And I think you said you used some of those drawings in your book.
Yeah, so some for which we couldn't get the copyright, my partner, who is an artist, actually redrew. And she said it was so difficult to do this well. Yeah.
Oh, that's fantastic. I appreciate hearing that story because he's a remarkable contributor.
Yes.
Okay, now let's turn to one of the more profound challenges in quantum physics, the Schrödinger equations, developed by Erwin Schrödinger almost 100 years ago now. provides a
Yes.
precise mathematical description of quantum behaviors, but it only provides probabilities for the possible outcomes of quantum events. So if you believe physics is causally determined, as most of us did once upon a time, then this is very unsettling. And one of the key milestones in that debate is what's known as Bell's theorem. That goes back almost 60 years ago, which demonstrates that quantum physics is indeterminate. And this is the topic of your prize-winning FQXI essay on undecidability and indeterminism, which is, again, cited in the show notes. So as simply as you can, tell us about Bell's theorem and the proposal to rescue determinism through these things called hidden variables. Just fill us in on that discussion point, that debate.
Yeah, good question. I'll try, and it's not easy because Bell's paper has more than 10,000 citations, and I would say there are also about 10,000 opinions about what it means. Everyone would say it's very simple and this is what it means. And I'm one of these 10,000 people, and I can't represent the entire literature, but the way I take it is as follows. It basically establishes a contradiction between assumptions that are very natural to make about physical theories and that before quantum mechanics were unchallenged. And I would say Bell was not the first to give this type of analysis. It goes back to a paper by Einstein, Podolsky, and Rosen in 1935. So it's really Einstein and his colleagues who launched the kind of reasoning that Bell basically completed. And as I see it, but again, many people say different things, it establishes the impossibility to say that physics is both local and deterministic and compatible with quantum mechanics, plus a fourth assumption I will state later, because Bell initially, I think, overlooked it. But the first few ones, as you said, quantum mechanics via the Schrödinger equation and what we call the Born probabilities makes probabilistic predictions only. So you can't say what the outcome of an experiment or a measurement is for certain. Quantum mechanics doesn't say that. It just says that this is possible and that is possible and that is possible, and it states the probabilities for all these possibilities. Now, if you would like a deterministic physics, you would say that quantum mechanics is not complete. That's what Einstein said. It misses something. So there's a hidden part in nature that is not captured by quantum mechanics. It's as if the president hides information from Congress. It's there, but it's sort of not known. And so this is a logical possibility, that there are aspects of nature, called hidden variables typically, that quantum mechanics misses, and that would be very, very hard to unearth, but are there. So that's an assumption you could make about nature, and then Bell gives conditions if that is possible. And so the main condition that he states is locality, which will be excluded by his theorem, and that has to be said or explained in a very, very precise way. So as follows, I hope you have time to listen to this, because otherwise it doesn't really make much sense. So there are always two parties, which are called Alice and Bob, although these are not names that either Einstein or Bell ever used. This is sort of modern terminology. They're experimental physicists, they're wide apart, and they do experiments. And so the locality assumption that Bell's theorem challenges is as follows. Assuming determinism, so assuming there is this hidden part of nature missed by quantum mechanics, but assuming it's there, then the outcomes of experiments are determined, and the locality assumption is that the outcomes of Alice's experiments cannot depend on the choice of experiments by Bob and vice versa. And this is subtle. You can't say her outcomes do not depend on Bob's outcomes, because typically they do. But in quantum mechanics, and this was clear to people like Bohr and Heisenberg right from the start, it matters enormously which experiments you do. And if you do one, you can't do another. If you have a particle, you can't measure both position and velocity or momentum, etc.
Let me pause here for a second, because the simple way I understand this is to think about what are called paired particles. So you have a quantum event that produces two particles. You know they share the same physical characteristics, for example, of spin. And from this event that occurred, they go off into different directions. One of them that way, the other way, and Bob gets the chance to measure the spin of one of those particles, and Alice gets to measure the spin of the other particle.
Yes.
And it doesn't matter what order they measure them in. It turns out that they will both measure the same outcome, even though it was indeterminate. It could not be determined, and it wasn't causally determined at the point those particles were created and started moving off. So the locality provision is the one that says, well, there had to have been something at the time that event occurred, because once they're on opposite sides of the universe, one cannot communicate to the other faster than the speed of light. Right?
No, that's right. Everything you said is right. It would have been the next level of my explanation, which is now unnecessary. But especially in that situation, they have a choice. So you have particles with spin, and they can measure spin, let's say, in the x direction, or in the z direction, or in the y direction. And these measurements are incompatible. They have to do one, and they cannot do the other. And so either Alice and Bob make the same choices, which is the situation you describe. So they both measure the spin, let's say, in the up or the z direction, and then they will always find the same outcome. But this was actually what Einstein, Podolsky, and Rosen already noted. So you basically gave their analysis. And this led to his famous Einstein's debate with Bohr, and they sort of got stuck in who was right. So Einstein claimed that this showed that quantum mechanics was problematic and there had to be a deterministic layer. Bohr denied this, and they both died, and the argument was unresolved. And so what Bell's contribution was the idea that also Bob and Alice could measure different directions for spin. Like Alice could measure the horizontal or x direction, and Bob could measure the z or the vertical direction. And then you get a very interesting mathematical situation. That leads to Bell's theorem. And then, so Bell showed at first sight that is a combination of determinism, of the fact there is a hidden layer in nature missed by quantum mechanics, but which is there. This very specific locality assumption that I try to detail, and the predictions of quantum mechanics, which are statistical, cannot all be valid. That's basically his theorem, but it turned out much later that he himself made a hidden assumption that was basically unearthed later. To really get a contradiction, you have to add a further assumption, which is sometimes called free choice or even free will, and which means that the choice of measurement by both Alice and Bob is independent of the state of the system that they measure. And this is usually taken for granted. It's what it means to do physics, some people would say. But in the technical and mathematical analysis, that is really an assumption you have to make. And this became clear since after Bell's theorem, people tried to sort of circumvent it. So again, this contradiction is between the statistical predictions of quantum mechanics everyone believes, the assumption of determinism, the assumption of locality, and the assumption of free choice of experiments. And so I would say the first attempt to circumvent this was by David Bohm. It's called Bohmian mechanics. It gives up locality. So it's compatible with Bell's theorem, and of all the possibilities, it gives up locality. And then you have a deterministic theory called Bohmian mechanics that reproduces quantum mechanics. Well, we will discuss later if that's really the case, but that's what people believed. And then the other way, the other logical possibility, followed by the Dutch Nobel Prize winner Gerard 't Hooft, who was one of the leading particle physicists of the 1970s and 80s, but he also worked on the foundations of quantum mechanics. And he proposed a local deterministic theory, which he called the cellular automata interpretation of quantum mechanics. And then people just derided him, saying that this is impossible and it violates Bell's theorem. But in that light, it became clear that his theory violated this free choice assumption. But it was local, and it was deterministic, and it did satisfy the statistical predictions of quantum mechanics.
Right.
So just to finish it, you can break in. The whole idea of these hidden variable theories is that quantum mechanics comes out when you average over the unknown or hidden state. And this is possible in all these sort of both Bohm and 't Hooft, and there are other possibilities too. And this is the view I challenge myself.
Right. So I would just want to back up a second to clear that up with my own words. So the two loopholes to Bell's theorem that would potentially allow determinism to survive quantum mechanics were the idea of the non-locality of those hidden variables, like the perhaps some warping of space-time that would allow some communication between locations in different parts of the universe, or what Bohmian mechanics, which I don't understand. So there's a possible loophole there. And the other loophole is to say that, well, really, Bob and Alice don't have free will, and it's already determined at the beginning, so they end up doing what they are determined to do rather than having free choice. And so that opened the possibility of, Bell's theorem, quantum mechanics, and determinism. Yeah. And your essay, the FQXI essay, makes a demonstration that that's not possible. And so tell us how you went about that demonstration.
Yeah. So I thought about what it actually means to reproduce the statistical predictions of quantum mechanics. And in the case of Bell's theorem and similar results, what it is taken to mean is that the average probabilities that come out in long runs of measurements, so typically these Alice and Bob experiments are repeated really billions and billions of times. And you have various outcomes with various probabilities, and these probabilities are determined by averaging. So if you compare this with a coin flip, so suppose we have a fair coin, equal chances of up and down, and you throw it maybe 1,000 times, and then you count the number of heads, which will be approximately 500, and you count the number of tails, and it will be about 500, and you say on that basis, the probability of heads is 50%, or 1/2, as we say. And so is the probability of heads. So that's one way to look at the statistical predictions of quantum mechanics. You take a long run of measurements and you average, basically.
Yeah, and you talk about that as the frequentist.
That's
you look at the frequency, you average it, and you say, all right, well, I've done 1,000 of them, and it should come out to 500 heads and 500
so that was used by Bell in a very creative way by using these correlated states. But there's another thing, and this is what my work focuses on. You could take the outcome sequence of a measurement run by itself. So again, taking this example of throwing a coin 1,000 times, you just don't count how many ups and downs or heads or tails there are. Let's call them zeros and ones. The binary situation is enough. So you just don't count the number of zeros and the number of ones in the outcome. You just write them down: 0, 1, 1, 0, 1, 1, 0. You just write down 1,000 numbers. They're zeros and ones. And then it turned out, and that was half of my proof, so to speak, quantum mechanics does much more than predict that the average is 50% of zeros, and the average of 1 is 50% in an Alice and Bob typical kind of situation. It actually gives very specific predictions for the kind of pattern of this sequence of zeros and ones. So I used sort of more delicate, more refined predictions of quantum mechanics than just the probabilities. And here you can see that there are many more possibilities when you're open to studying the entire outcome sequence. For example, you could have 50% of zeros and 50% of ones in, let's say, a really random way. There's 0, 0, 1, 0, 1, 1, 0, just what we would all agree to be a somewhat random pattern. We could make it technical later on. Or you could have an outcome sequence like 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, etc. That would also have the right 50-50 probabilities, but it's not what quantum mechanics actually says. And Bell's kind of analysis doesn't distinguish these two cases. Bell only looked at the probabilities obtained by averaging and counting frequencies. And so the key to my work was to look at the outcome sequence as a whole. And then it turned out that in the 1960s, various mathematicians, of whom I think Kolmogorov is the most famous one. In the US, also Gregory Chaitin made a large contribution to this field called algorithmic randomness. These mathematicians actually studied what it means for a sequence to be random. And this is not so easy, in fact. So I tried to give an example, and I said we all have a feeling of what it means for a sequence to be random, and 0, 1, 0, 1, 0, 1, 0, 1, etc. is not a random sequence, but it's a technical sort of achievement of these mathematicians to actually define what it means for a sequence to be random.
So that's an explanation, I think, of something that is more random, if you will, than simply having an average that over a long sequence of trials approaches a certain result that you would expect if the coin tosses were random. And
no, that's right.
I want to take a second and ask about a follow-up about that Kolmogorov or algorithmic complexity. How does that relate to kind of the idea of computer algorithms?
Yeah, so that was in fact Kolmogorov's vision or idea to relate these things, which was completely new at the time. And this, you used the word complexity, that's why we're in your podcast. This is the complexity part, so to speak. And so Kolmogorov's idea was that the randomness of a long sequence of zeros and ones, for example, should be defined via the complexity of the computer program that could produce such a series. And so basically his idea was that a sequence like 0, 1, 0, 1, 0, 1, etc., however long it is, even if it's repeated billions of times, can be produced by a very, very short computer program, saying just print 0, 1, 500 million times, and you have it. So that's not a complex series, it's not random. And then what he proposed was that a truly random series could not be produced by a computer program except by simply printing it. And so I like the analogy of paintings. So if you take two very famous paintings, there's this black square by Malevich, the first so-called modern painting. It's just a black square, and if I tell you it's a black square, you have some good idea of what it is. If you take paintings by Jackson Pollock, and my favorite one is called Lavender Mist, but it applies to many of his works, you cannot describe these paintings except by seeing them. I could not describe any of his paintings of this dripping phase. And so from this Kolmogorov point of view, the paintings by Pollock are typically random. The only way to describe them is to have them in full, whereas the way to describe non-random sequences is to compress them. So another way to say this is that a random sequence is incompressible. it has no patterns that allow you to compress it without any loss of information.
Right.
You also have this in music. So classical music is typically very compressible because there's so many harmonies and patterns, whereas what's often called modern music has to be listened to. You cannot compress it in a lossless way. So that was Kolmogorov's genius, to actually define randomness.
Yeah, pardon me. I just I have another analogy that is sometimes helpful for people in understanding this algorithmic complexity. And one way of thinking about it is that, the computer algorithm will allow you to find a shortcut of how to make that string of numbers, for example, or string of data in a shortcut rather than having to list them all out there. So that shortcut is a kind of compressibility. You can make an algorithm that's a lot simpler than just the list of the strings, but something that's really random, you will not be able to find that, and it will be uncompressible, as you said.
Yeah, that's exactly right. And to strengthen this and to illustrate how subtle the situation is, if you take pi, the number 3.14, etc., if you look at the statistical distribution of the decimals or the digits, it looks very random, and it has survived all randomness tests imaginable so far. And yet it's non-random in the sense of Kolmogorov, because you can compute every decimal of pi with a very short algorithm or a very short computer program. So the 010101 example I gave was the simplest, but even pi is an example of a non-random number despite appearances. And so that's the strength of Kolmogorov's number, and also the difficulty. It's very hard to actually prove that the number is random or non-random.
Yeah, there's a way of, I think, as you describe it in your paper, you take segments or sections of the infinite string that you have from these quantum events, and you can look at each one of those segments, and if all of the segments you look at and continue to look at are non-compressible, that gives that property of randomness for that infinite string. Is that the way that works?
Yeah, that's right. But proving that even the finite segments are incompressible is impossible. So one of the amazing features of this analysis, and also the key to the result that I proved, is exactly that for finite random sequences, if you're given one, you will not be able to prove its randomness. So there's a really crazy situation that you can actually show that the overwhelming majority of both finite and infinite sequences are random in this sense of Kolmogorov, but you cannot give a single example. And if you are given a candidate, you will not be able to prove that it is random, although, again, the overwhelming number of sequences is random. And that was actually the key to my theorem. So that's the property that a deterministic theory can never reproduce. So this unprovability of randomness, that's really what contradicts determinism and makes deterministic theories underlying quantum mechanics impossible. So there are two sides to my proof. One is that quantum mechanics actually does produce random sequences in the sense of Kolmogorov that we discussed. And the other half of the proof is that no deterministic theory could reproduce this. Although a deterministic theory could reproduce these averaging probabilities. But if you look at the sequences as a whole, as this sort of global property of randomness, that's what a deterministic theory can never reproduce, whereas quantum mechanics does.
And that's a real contradiction. Yeah, that's a demonstration that was not possible 50 years ago.
No, that's right. And that has nothing to do with locality or Alice and Bob. It's enough to just have Alice or Bob. And this whole idea of EPR correlation is unnecessary.
Yeah. So that's an interesting relationship between the physics and the confusions that we've seen in physics, and then a later development in mathematics, which provides an additional way of looking at randomness. It's not merely indeterminate, but it is it is random under the definition Kolmogorov complexity.
Oh, exactly.
Yes. Well, but the other part of it is that determining whether something is random is unprovable.
Exactly. You summarized this extremely well.
Yeah, that's difficult. It's very hard to follow.
You're doing a great job. So.
Yeah. And so I want another concept that's been argued a lot over the century is what's known as Laplace's demon.
Yes.
The idea that if you knew all of the starting points of every particle in the universe, and then you run the mathematics out there, you would be able to predict the future. It's a deterministic process, like billiard balls on a billiard table is deterministic, and that was known as Laplace's demon.
Yes,
that would be able to make that determination. But your proof really shows that's not possible. That's an illusion. And
I wouldn't say that. It's not possible and consistent with quantum mechanics. So my proof has two sides. So one actually uses what we call the Born rule, the exact mathematical description for quantum mechanical probabilities in the more refined form given by John von Neumann. That's one half of the proof. The other half of the proof is this algorithmic randomness theory. And so the way I see it, if you give up the Born rule, so if you actually give up the idea that the statistical or probabilistic predictions of quantum mechanics are exactly right, then the proof breaks down, because this is what I assumed. And then you could have deterministic theories underlying quantum mechanics. And I even believe that that's the case. So I personally think that quantum mechanics is not the final word, and maybe even for the reasons Einstein said. But people like Einstein and Bell and everyone looking at this question still assumed that these probabilistic predictions were exactly right. It's funny, but you can actually state that statistical or probabilistic predictions are exactly right. This is a meaningful statement if you average over long runs of measurements. Right. But once you surrender the Born rule, once you surrender the exact mathematical expression for probabilities, so my argument breaks down, and there could be a deterministic theory. And that's what I think, because I believe quantum mechanics is actually emergent from sort of a lower lying or more fundamental theory to be discovered.
Yeah, that's interesting, and you don't go into that in your
no, that's right.
Paper, but the idea that so let me see if I can put some common words around it. It's like the Born rule says the probabilistic outcomes predicted are exact, and you're saying that maybe that rule needs to be abandoned or set aside, and the analogy might be that rather than being exactly perfectly probabilistic in the way described, maybe there's some sort of a wobble or wiggle or something that's not necessarily, hasn't been found yet, hasn't been discovered, but something that would still recover the determinism that you feel is in place. Is that a fair characterization?
Yeah, exactly. And it's simple what could go wrong. Suppose that, so in quantum mechanics there is the idea of a fair coin toss. You can make devices, these are quantum random number generators you could actually buy commercially. And they claim to give random sequences of zeros and ones with exact 50-50 outcome probabilities. Now, suppose that in fact these outcomes are 0.49999, etc., stopping at some point, and the other is 5.00001. That would already break the Born rule. It could be just a mistake in the 20th decimal in the Born rule. That's enough to violate my proof. I need the exact probabilities as given by quantum mechanics for the argument to work. It wouldn't really challenge the usefulness of these quantum random number generators. They will still be random for all practical purposes. Mm-hmm. But for the kind of fundamental reasoning that I used, and also that Bell used, this would be enough for the argument to break. And so if there is this underlying theory, it need not reproduce the exact probabilities. It must, in fact, deviate from them. And this it could do at any level, the 10th decimal, the 100th decimal. Any violation invalidates my proof. And so I see ample possibility for determinism.
Yeah, is that ultimately, do you believe that the determinism or indeterminism is going to be provable?
Well, no, I don't think it's ultimately provable in an absolute sense. So you could always have theories succeeding each other, where one, like quantum mechanics, has the appearance of indeterminism. As you know, quantum mechanics in some way gives rise to classical physics. In fact, I wrote a 1,000-page book about that. So quantum mechanics by itself, in its official probabilistic version, still manages to reproduce classical physics in a certain limit. So you can go from an indeterministic theory to a deterministic theory. You can go from a deterministic theory, like a hidden variable theory, to an indeterministic theory, like quantum mechanics. And this could go on and on and on.
So you see this as an open field for future research, and
oh, absolutely.
Yeah, and will there ever be a final answer?
No, I don't think so. But this in itself just distinguishes myself from most people. If you take a field like quantum gravity, often seen as the holy grail of theoretical physics, everyone working in quantum gravity takes quantum theory as given, including its exact probabilistic predictions. Except Roger Penrose. Another reason to admire him, he's one of the very, very few people to say that actually you might need to change quantum mechanics. I think quantum gravity people typically assume quantum theory and change gravity or general relativity. So Penrose and also we say the opposite. Let's engineer quantum mechanics one way or the other and make it compatible with relativity.
Yeah. Klaas, you almost have me convinced.
Good.
We're close. Okay. I want to change gears a little bit and talk about another of the puzzles of modern physics, and that's known as the fine-tuning problem. And you have a very nice article on this. It's in the show notes. It's called The Fine-Tuning Argument. So just what are some of the facts in observed facts in physics that lead people to conclude that the universe has these very, very unique characteristics, like one-of-a-kind, unique characteristics?
Well, yeah, so this question has two sides. Let's take the one that's easy to answer, namely which parameters or facts are in fact believed to be fine-tuned. And the really difficult question is, fine-tuned to what? To life with the biochemistry we know, or just to the existence of galaxies, which is already non-trivial, the existence of planets. So that's a difficult question to what we fine-tune. But the things that do the fine-tuning, I think, are easy to explain and less controversial. And there are two sides, and that makes this incredibly interesting. So part of cosmology is fine-tuned, and part of particle physics is fine-tuned. So if you take elementary particle physics, let's say the quantum mechanics of the very smallest distance scales we have science about, and we have the cosmos that is also fine-tuned in a completely different way. And in fact, the cosmological fine-tuning is easier to explain, I think. If you take the average density, matter and energy combined density of the universe as it is now, and calculate it back to what it was, this we can do, just a little after the Big Bang. Then it turns out that at that time, if this matter and energy density had been 10 to the minus 50 different, by an incredible small margin different, if it had been smaller than what it is, the universe would have expanded very quickly. There would be no stars, no galaxies, no life. If it had been ever so slightly bigger than what it actually was, then there would be more gravity and the universe would have recollapsed very quickly, and there would have been no galaxies and stars and planets either. So this energy and matter density is one of these fine-tuned parameters, and the deeper you go back in time, the higher the fine-tuning, and let's say after 1/10 of a second, it was fine-tuned to an incredible degree. So that's, I think, still the best example. Either we would have recollapsed immediately, or we would have expanded so quickly that there would be nothing, like structure.
Right, and that's an example if we go to complexity science, where we talk about chaotic systems that are very, very sensitive to initial conditions.
Yeah, so you have this.
We only know the conditions. Yeah, we only know the conditions back to very close to the Big Bang, but those initial conditions were very, very remarkably fine-tuned so that the universe we live in today came about. Yeah,
but to finish the argument, on the other side, on the microscopic side, I mean, even if the cosmology is correct, is as it is, so that we're here to talk, I mean, if, for example, the masses of the up and down quarks or some of the strengths of the fundamental interactions had been slightly different, for example, the quark masses have been very well studied. If they would be different by, let's say, 1 order of magnitude from what they are, and it's especially the mass difference between the up and the down quarks, then there would be no nuclear fusion. That's part of the electroweak interaction, as we say, this process. And there would be no stars and no galaxies, and it would all have been completely different, and we wouldn't be here. And there are other cases. So there's fine-tuning in the microscopic parameters, and there's fine-tuning in the macroscopic parameters. And they both, I would say they work independently, but they both work towards the same idea of fine-tuning.
Yeah.
And at
this point, there's no theory that pulls all those together to say that, this is why these things are the way they are. It's simply the observed nature of this universe we're in has these characteristics. These characteristics were essential to the formation of stars and galaxies and the formation of the elements of carbon at a certain thing, and subject to certain that created an environment and at least one planetoid that resulted in the development of higher biochemistry that started self-replication and all that sort of stuff. And, bingo, we ended up with life, and we ended up with, evolution, and we ended up with people. And here we are pondering these issues.
Now, I agree.
I don't know
mostly. Except, I think on the elementary particle physics side, this is completely correct, what you're saying. On the cosmology side, there still is the idea that this theory of inflation actually solves the fine-tuning problems in cosmology, which may be the case, but these inflationary scenarios themselves have to be fine-tuned to an extent that is even more spectacular than the fine-tuning in cosmology that they're supposed to solve. So inflation is still unclear whether that has happened or not, but even if it's correct, it has its own fine-tuning problems, and the problem is just moved.
Yeah. So you in your essay you talk about 5 different ways of thinking about this problem of fine-tuning, and I wonder if you just walk us through those five possibilities.
Yeah. So the first possibility is design. I mean, that's a very old Christian, also Jewish argument, and I'm sure other civilizations or religions had similar ideas. That simply there's a creator who created the world in exactly the way it is, with the goal of being as it is, and especially of humans to live and believe in God, so to speak. So the argument of design, technically you have the argument of design and from design, but that's secondary. So the idea of a creator, let's say, with a goal and a will. That's a possibility. The other possibility is, I think, favored by most secular physicists. It's called the multiverse. That means that, yes, this universe is fine-tuned, but it's just one in a collection of innumerably many other universes. They all have different parameters, and well, one had to be, because there's so many of them, one had to be right for life, and of course we're in that because we couldn't be in any of the other ones because there is no life. I mean, the logic of this argument is suspicious, I think, and also there still is no good theory that gives rise to it. So inflation gives rise to a multiverse, but is extremely speculative and has to be fine-tuned. So there's this landscape idea in superstring theory that gives rise to a multiverse in a way, but string theory also is extremely speculative and unproved. So I myself don't take the multiverse seriously, but almost everyone you would interview who knows modern physics will point at that as the solution. So here I have really a minority view. I'd rather have design than that. Mm-hmm. Mm-hmm. So that's the second one. The third one, I would say, is blind chance. It's in a way similar to the multiverse, but you can also have it if there's just a single universe. So if there is a single universe and you believe there are all these possibilities for the parameter values in particle physics and in cosmology, well, it could simply be that it's like the way it is without any further explanation. So things happen in life without further explanation. So that's the way it is argument. Okay, the fourth one, which I call blind necessity, I also use the word blindness, means what Einstein felt was the case, that the laws of nature are fixed, including the values of the parameters. So he would say, in fact he wrote this in one of his last essays in 1949, he wrote this explicitly. He said, well, we have laws of nature that we know to some extent. They have parameters that with our current knowledge are free. They could have another value as far as our knowledge is concerned. But in fact, if we were to know all of physics, we would fix the parameter values. There's no choice at all. This is also basically what Spinoza said. Had he known modern physics, he would have used the same argument. Mm-hmm. And I call it blind because both Spinoza and Einstein would say that although it's sort of necessary, there's no design behind it. Again, it's the way it is. But it's different from blind chance. Mm-hmm. And then the fifth way, so to speak, is that the whole problem is misguided. And I tend toward that. As I can explain if we have time, but this is what I really believe, that the whole fine-tuning problem is really a bit of a non-issue. It's been sort of
I think you suggested in your essay that it's a good candidate for therapy.
Yeah, so this I learned from Wittgenstein, this point of view, that philosophical problems are not problems. They're reasons to go to a therapist.
Yeah. Let me ask you, this is a speculation. Certainly many people before Darwin had all sorts of concepts about why there were bones in the earth and, yes, dinosaurs and, how things came to be the way they were. And Darwin was able to explicate the process of,
yes,
mutation and natural selection. And is there a possibility that the problem of fine tuning is really something like that in the context of the early moments of the existence of the universe, we still don't know first cause, but in the early moments, there were processes in play in terms of breaking of symmetry under conditions, and then an emergence of properties that were selected, essentially among alternatives in an evolutionary sense, not a deterministic sense, not in a deistic sense, but just a set of processes that evolved in a certain way and certain properties emerged with those particular, and then this cascading process of the emergence of the universe ended up following a pathway that was laid out through the emergence of these constants that yielded a universe. So maybe it's a little bit like blind necessity, but it's a process of emergence that we can't describe. Does that make any sense?
Yeah, so I learned this point of view from Lee Smolin, who's one of the physicists working in one of the leading people in quantum gravity. And so on the one hand, I sympathize with mechanisms like that, but I also feel they go somewhat beyond what we can ever know. So in my own work, I stay close to the facts, and scenarios like that are so speculative and go so far beyond not only what we know, but I think what we even can know, that we would never be able to prove such a scenario.
Yeah.
But again, I sympathize with it.
Yeah, a favorite quote of mine from Wittgenstein at the end of the Tractatus is, "That whereof we cannot speak, we must remain silent."
Yeah, I'm on that side. Although, again, I admire physicists who are not silent, but they seem to overestimate the power of the human intellect.
Yeah,
I think.
Yeah. The balance between humility and hubris is often
exactly. It's on the wrong side.
Yeah. So I'd like to change gears again and go in a different direction here. Klaas, were you raised in a religious tradition?
Yes. So my parents were Roman Catholic at a time, so this is the 1930s and 1940s, that even in Amsterdam, they met the first non-Catholics only after they were 20. So they were in a closed community. The Catholics went to the same schools. They had their own sports clubs. They had their own dancing societies. And that in a place like Amsterdam, it's really remarkable. And so I was raised in that tradition, although when I grew up, which was in the 1960s and 70s, there wasn't this isolation anymore. But I still went to a Catholic. I was educated by the Jesuits. Like the current Pope is also a Jesuit. Mm-hmm. But interestingly enough, when I was about 12 or 13, my parents actually were knocked off their faith by a certain preacher who is well known in the Netherlands called Oosterhuis, who was a Jesuit himself, who had married and had been expelled from the Society of Jesus, from the Jesuits, and as some sort of a revenge, maybe, he started his own church. And he was a good theologist and a fantastic preacher. He wrote his own songs and hymns. And so half of Catholic Amsterdam actually went to him, like a flock of sheep. He's still alive, in fact. And so slowly he changed the nature of Catholicism in the Netherlands. And so he himself would state that he's religious, but that's not what he brought across. So the people he brought to his church lost their Catholic faith, but didn't sort of re-enter it through the back door as he had done himself. And so my father died 5 years ago, and during his last year he had stomach cancer and was determined to die, so to speak. And I talked almost every day with him about his life, and he felt increasingly frustrated about his Catholic youth, and especially about the dogmatism. Mm-hmm. And so this preacher, Oosterhuis, had opened his eyes to the possibility of a non-dogmatic way of believing, and that led to not believing. And this irritation with the dogmatism of the Catholic Church I share. So I don't see myself as an atheist, but rather as a sort of a mysticist. I'm searching, I'm groping. But I wouldn't want to enter any religion that is dogmatic.
Yeah.
As the Roman Catholics, I think, still are, in many ways, based officially on a series of dogmas.
Yeah. It's interesting that the Jesuit tradition has a reputation for a commitment to science and inquiry.
Oh yes, I had great teachers. Yes.
Yeah, and many Jesuits have sort of drifted off for the same reason, I think, because of the dogmatism the Central Church can be.
No, they're admirable. If you look at the history of the scientific revolution, so the Jesuits played a role just a little bit before Galileo. They were the first to use mathematics in physics, for example. Yeah. And they had an observatory in Rome, which was important.
Yeah.
So I have that side too.
Yeah, and I think reading from I think it might have been in the preface or introduction of your textbook, you started early in the study of math and physics. So there was a certain amount of passion that drove you into the field.
Yeah, to be honest, in my youth, I mainly played chess. So half of my childhood between, say, 10 and 20 was devoted to playing chess. But so between the lines, I did read books by Einstein and Heisenberg and Bohr, also Bertrand Russell. And I had this passion, at least chess is also an exact game. It has very precise rules and you have precise strategies. And then I left chess for mathematics and physics, so to speak. Mm. So I had that passion also for books and for learning very early.
Yeah, even though chess is a deterministic game in a certain sense, it also drags you quickly into complexity.
Yes, it's a complex game. Come to think of it, since we discussed John Bell and his theorem, a book I remember from my childhood is called The Dancing Wu Li Masters by a guy called Gary Zukav. And it's about the relationship between quantum mechanics and Eastern-style spiritualities, like the Tao of Physics by Capra. And this book is actually very good. I mean, he explains Bell's theorem very well. That I also read when I was maybe 15 or 16, and it drove me into theoretical physics.
Yeah, well, that's a wonderful pathway. So you seem quite comfortable with. It sounds like you have an ultimate belief in the determinism of the world we're in, but the fact that right now there's no clear pathway to define that or prove that, and so we live in this uncertain, indeterminate place, but you seem to be comfortable with that and with the pursuit of these bigger questions without getting sort of existentially challenged or concerned. Is that a fair?
I don't feel comfortable at all with this. It's interesting that you believe that on the basis of what I write. I just like to figure out the way the world is, and if you compare this with studying history, human history, I'd like to figure out how it is or how it was. But I don't feel comfortable at all with human history. And it's similar with physics. And I would say neither a deterministic nor an indeterministic world would make me feel comfortable. I live in existential angst. Mm-hmm. And I would say that doing this kind of physics that I do, sort of fundamental science, is an escape route from this existential angst. So I don't feel comfortable at all. Except by actually figuring out how things work, but then the results feed this angst.
Yeah.
So it's not so easy.
Yeah. So you said earlier that you perhaps had was the word mystical?
Yeah, I see myself as a mystic. Yeah, mysticist. Okay. So I believe there's this huge mystery we will never be able to penetrate or understand. Yeah. That's my core belief.
Like the first cause. I mean, we may have a pretty good picture of the initial moments after the Big Bang, but it's never going to be. How can you ever answer the question of a first cause in that?
No, that's right, and so I believe that the great religions do not have the answer to this point. Mm-hmm. Otherwise, I would be a believer and maybe still a Catholic even. But I think it's at a level that is totally inaccessible to us, the explanation.
Mm-hmm. Mm-hmm. So I have a last question I like to ask my guests, and that's, I like the way you put that in terms of the mystery that's here, and you're pursuing these questions because it's one way of alleviating the angst of those questions. Have you ever had a personal experience yourself that felt magical or mystical, something that influenced your life? You don't really have a good explanation, and but it just feels like it was really important.
That's a great question. So I'm divorced, and the way I met my current wife was incredible. So we met on a boat during the Corona period. It was extremely unlikely we would be on that boat at the same time. We were wearing face masks. We were even separated by something like a plastic transparent curtain, so we couldn't even see each other well. And nonetheless, we did see each other, and so now we are the happiest couple you could imagine. also many sort of fine-tuned details are exactly right in a way that is almost unimaginable and suggests. You see, in the Jewish Orthodox tradition, these people have matchmakers or brokers, and I mean, even the best broker wouldn't have been able to accomplish this.
Yeah.
And this is magical and incomprehensible, I think.
Yeah. And there's no algorithm that could possibly be invented.
No. If I had gone to a dating site which uses algorithms after my divorce, this would never have been the outcome.
Yeah.
It's pure magic.
Well, Klaas, thanks you very much. This has been a wonderful conversation. You've taken us on quite a journey, and I really appreciate your candor, your openness, and the joy that you have both in your current marriage, as well as in the pursuit of these wonderful questions. Thanks for joining me.
Well, thank you. It was a pleasure to have this conversation. I've said things I've never said to anyone before, so there you are.
Thanks for joining us on this episode of Making Sense of Complexity. We'll be taking a break. In the meantime, please explore the websites of our collaborators Complexity Adventures, Planksip, and Talk of Today, and join the conversation on our social media outlets or on spiralinquiry.org. Be sure to subscribe so you don't miss the next episode. Stay well and have a great week.